Hello and welcome to yet another lecture on the binomial theorem. In the previous lecture, we looked at some series involving the binomial coefficients, and in this lecture, we will look at a few more identities based on the binomial coefficients. So, today's first example is going to be to evaluate c0 square plus c1 square and so on to cn square. Once again, the first step is to write out the general term of this series, and that's just going to be cr square, and you have a summation r equals 0 to n. I'd like to remind the viewer once again that we use the notation cr for ncr. So, in our previous lecture, all our series involved linear sums of CR in some sense, but in this lecture we are going to be looking at products of CRs. So in this case we want to evaluate summation CR square. So most of our previous lecture, the idea was to somehow use the expansion 1 plus x to the whole power n to somehow get the general term we are looking at in the coefficients of this expansion. So this time around, since we want CR square, intuitively we would like to multiply 1 plus x whole power n with some other sequence to get CR square. So let's write out 1 plus x to the whole power n in more explicit form. So we could write 1 plus x to the whole power n as c0 x power 0 plus c1 x power 1, so on till cr x power r, so on till cn x power n. So another way of writing the same expansion, as we've seen in our previous lectures, is 1 plus x to the whole power n is cn x power 0 plus cn minus 1 x power 1, and so on to cn minus r x power r, and finally we have c0 x power n. So if we're trying to generate CR square, then we could generate CR square by multiplying these two expansions and looking at an appropriate power of x in the resulting expansion. So to obtain CR square, we would want to look at, we have CR x power r here, and we have CR appearing as the coefficient of x power n minus r in the second expansion. So to obtain CR square, we would want to look at the coefficient of x power n. So we are looking at the coefficient of x power n in the product 1 plus x power n times 1 plus x power n, and on the right hand side we would obtain CR square for each choice of r, and that gives us c0 square, c1 square, and so on till cn square for different choices of r. So the right hand side is going to give us summation r equals 0 to n cr square, which is obtained by this result we had earlier, and in the left hand side we're just looking at the coefficient of x power n in 1 plus x whole power 2n. And we know from the binomial theorem that this is nothing but 2n cn. So the result is that we have summation r equals 0 to n, cr square is 2n Cn. So this is the result that we seek. So once again, the idea when we want to obtain products of binomial coefficients is to multiply the expansion of 1 plus x to the whole power n, or in general multiply any suitable expansion with another expansion, and to look at the coefficient of a certain power of x to obtain the terms of the sequence we so desire. So in this case, we multiplied 1 plus x to the whole power n with itself, and we wrote 1 plus x to the whole power n in two different ways, and we looked at the coefficient of x power n in the resulting expansion to evaluate summation CR square. And the final result is that summation CR square is 2n Cn. So let's look at another identity based on the binomial coefficients, and this identity is asking us, this problem is asking us to evaluate 1 times C1 square plus 2 times C2 square, so on till n times Cn square. So we can write out this summation as summation r equals 1 to n r times CR square. So if you recall from our previous lecture, we looked at how we could obtain RCR as a coefficient of a certain expansion, and so we can write that out once again. So we had n times 1 plus x the whole power n minus 1 is 1 C1 x power 0 plus 2 C2 x power 1, so on to RCR x power r minus 1, and so on to n Cn x power n minus 1. So we have written RCR as the coefficient of a certain binomial expansion. The next term which we would like to write out is just CR, and again we can write CR as the coefficient of the expansion of 1 plus x to the whole power n. And let's write out the second form we wrote out previously. So we can just write this as Cn x power 0 plus Cn minus 1 x power 1, so on to Cn minus r x power r, so on to C naught x power n. So you notice that RCR is the coefficient of x power r minus 1 in this expansion, and CR is the coefficient of x power n minus r in this expansion. So when you multiply these two expansions, you get that r times CR square is the coefficient of x power n minus 1 in this expansion, and by varying r you would get the different terms in the summation. So we have that the coefficient of x power n minus 1 in n times 1 plus x whole power n minus 1 times 1 plus x whole power n equals summation r equals to 1 to n r CR square. So this right hand side is obtained by looking at the general term in these two expansions and looking at the coefficient of x power n minus 1. So to evaluate the left hand side, once again we can simplify it and use the binomial theorem. So the left hand side is nothing but n times 1 plus x whole power 2n minus 1, and you want the coefficient of x power n minus 1 in this term, and so that's nothing but n times 2n minus 1 c n minus 1. So we have that summation r equals 1 to n r times cr square is n times 2n minus 1 c n minus 1. So far we have seen two different problems which require us to use the binomial expansion of 1 plus x power n or its derivative and then multiply it with itself to obtain the summation of a closed form expression for a particular summation. So the following problem can be taken as an exercise. So in this problem you're asked to evaluate C naught CR plus C1 CR plus 1 and so on till Cn minus R Cn, and this is nothing but summation j equals 0 to n minus r cj times cj plus r. So a hint for solving this problem, which I'm not going to do right now, is look at the coefficient of x power n minus r in 1 plus x power n times 1 plus x whole power n. So if you look at the coefficient of x power n minus r in this expansion, you should be able to derive a closed form expression for this summation just given here. So it's pretty similar to the first part we've seen in this lecture. So the fourth problem we'll be looking at is an application of the previous results we've seen in this lecture, and it asks us to evaluate summation r equals 0 to 2n minus 1 power r 2n cr the whole square. And this is a multiple choice problem, and the four options we have are 4nc2n, 2ncn, minus 1 power n 2ncn, and D is none of these. So in general, for such an objective question, you cannot just plug in a few values of n and arrive at a final result, because you have the option none of these. Whereas if you had all four options to be based on binomial coefficients, then you could possibly weed out some of the options by plugging in suitable values of n and narrowing it down to one of the four options. So for this particular problem, we're going to actually work out what the summation turns out to be, and then conclude which of these options is the right result. So as we've seen in our previous examples, we would want to form 2n cr whole square from the expansion of a suitable term, but notice that we also have a minus 1 power r in this result. So as we've seen earlier, you can get 2n cr from the expansion of 1 plus x the whole power 2n in this case, and so we can write out 1 plus x the whole power 2n as 2n c0 x power 0 plus 2n c1 x power 1 so on till 2n cr x power r and so on till 2n c2n x power 2n. To get minus 1 power r times 2ncr, we realize that we've got to look at the expansion of 1 minus x the whole power 2n. And so let's write out an expansion of 1 minus x the whole power 2n. And this can be written as 2n c2n x power 0 minus 2n c2n minus 1 x power 1, and so on till minus 1 power r 2n c2n minus r x power r, and so on till minus 1 power 2n c0 x power 2n. So to obtain 2ncr the whole square, and to obtain, we obtain 2ncr from this term and 2ncr from this term, and also a minus 1 power r from the second term. So 2ncr is the coefficient of x power r in the first expansion, and minus 1 power r 2ncr is the coefficient of x power 2n minus r in the second term. We obtain a minus 1 power r since we have minus 1 power r is the same as minus 1 power 2n minus r, since 2n is even. And so we can obtain minus 1 power r 2ncr the whole square by multiplying these two expansions and looking at the coefficient of x power 2n in the resulting expansion. So we have that the coefficient of x power 2n in 1 plus x whole power 2n times 1 minus x the whole power 2n equals summation r equal to 0 to 2n minus 1 power r 2n cr the whole square. So we would like to evaluate the left hand side based on the application of the binomial theorem. And the left hand side is nothing but the coefficient of x power 2n in 1 minus x square the whole power 2n. So we would like to evaluate the coefficient of x power 2n in this expansion, and this is equivalent to evaluating the coefficient of y power n in 1 minus y whole power 2n, where we've just replaced x square by y. And so we now want to find the coefficient of y power n in 1 minus y power 2n by setting y equal to x square in the previous result. And so this turns out from the binomial theorem to be nothing but minus 1 power n times 2n cn. So we have that the summation r equals 0 to 2n minus 1 power r 2n cr the whole square is nothing but minus 1 power n 2n cn, and fortunately one of our options is minus 1 power n 2n cn. So the right result is c minus 1 power n times 2n cn. So that's it for this lecture. Hope you enjoyed watching it, and in the next lecture we will look at some more applications of the binomial theorem and derive a few more identities based on the binomial coefficients. Thank you for listening.